The time versus distance graph of PS and surface wave arrival times was constructed by analyzing thousands of earthquakes from hundreds of seismograph stations around the world. Here we show an earthquake near the top of the globe and graph the arrival times to seismic stations at varying distances from the hypocenter. The y-axis shows the distance from the earthquake and the x-axis shows the elapsed time since the event. The seismograms record the arrivals of the compressional P, the shearing S, and the rolling surface waves. Seismic waves travel at different rates, so the farther a seismic station is from an earthquake, the farther apart the P, S, and surface wave arrival times are. Here we show only the direct P and S wave paths through the mantle and crust. The final image of this animation will show more of the complexity within the Earth as waves are reflected, refracted, and damped due to changes at depth. Connecting the waves through a stack of seismograms creates the travel time curves that can be used to locate earthquakes. Simply stated, the time difference between the arrival of the P wave and the S wave can be used to measure the distance from seismometer to the epicenter.
In all the three dimensions. Let us consider an infinitesimal stress element which shows the state of stress at a point in the given stress body. Assume that the stress element is in equilibrium. We see that this stress element consists of 6 faces in the 3 dimensions. The face perpendicular to the positive direction is called positive face, and that to the negative direction is called negative phase. Now the stress element is subjected to 3 different normal stresses and 6 different shear stresses. Thus, to define stress at any point in a 3-dimensional space, we require 9 components of stresses, which can be represented in the form of a multi-dimensional array as shown. Such array is termed as a 3-dimensional stress tensor. Thus, a 3-dimensional stress tensor is a multi-dimensional array of 9 stress components. Now let's discuss about the nomenclature and sign convention.
Earthquakes generate 2 main types of seismic or shock waves: body waves and surface waves. Body waves travel through the interior of the Earth. The fastest of these are primary, or P waves. These compressional waves move faster in dense rock and slower in fluids. Thus, their speed and direction change. Because they are deflected by the Earth's core, P waves are not seen in the so-called shadow zone. The slowest body waves are secondary, or S waves. S waves are elastic shear waves that move material sideways at right angles to their direction of travel. Because secondary waves travel only through solids, they do not penetrate the Earth's outer molten core. For this reason, there is also an S-wave shadow zone. The slower seismic surface waves do not penetrate the Earth's interior, but follow the surface. One type of surface wave, the love wave, travels in a circular motion and causes damage by displacing materials horizontally. Love waves can be very damaging. This cracked pavement and these twisted railroad tracks clearly demonstrate their destructive power. Earthquake damage also results from Rayleigh waves, surface waves which deform materials vertically.
As Rayleigh waves travel in backward rotating circles, they cause the ground to accelerate through a vertical lift, a horizontal push, a vertical drop, and a horizontal push in the opposite direction.